All right, so today's science and engineering practice is patterns. Today we're going to talk about the difference between stable and unstable nuclei. We're going to be using a simulation activity to help us with this assignment. So you guys will need to print off this handout beforehand or use a separate piece of paper to take notes on what makes atoms stable or unstable. So let me show you kind of what you're expected to do. At the top it says, describe the phenomenon. So the phenomenon that we are observing is this activity, our simulation, and this simulation is going to show us stable and unstable nuclei. So I'm just going to describe that. Apologize, I'm trying to hold my phone and write at the same time, so my handwriting's a little shaky. Stable and unstable isotopes or nuclei. That's the phenomenon that we are investigating with this activity. Now on the side, step number 2 says, which kind of pattern have you identified? So today we're looking at a relationship between two different factors. We're going to talk about what those two different factors are that are being measured here in our simulation. The first factor is the number of protons in the nucleus, and the second factor is the number of neutrons. Those are the two factors that we are looking to see if there's some sort of pattern or relationship between. So in science, when we're testing a pattern between two factors, we can use a line graph or a scatter plot to take some data on this pattern. So you guys are going to make a scatter plot in the box here in our representation of this pattern. So again, when we set up our graph, we're just going to have an X and Y axis. So you're going to sketch that into your space. And again, I apologize. It's a little bit shaky. Okay, but on our X-axis here, we're going to keep track of the number of neutrons. So we're going to label our X-axis number of neutrons. And on the Y-axis, we're going to look at the number of protons. Okay? So you can see that you can adjust these two factors and it creates different nuclei on your screen as you adjust the number of protons and neutrons and click the play button. Okay? So for the number of protons, we are investigating elements between 82 and 92. These are all elements that have a high number of protons that are radioactive. And for the number of neutrons, our scale is going to range between 119 and 148. Okay, so you're going to want to fill in your axes, number all the numbers, and I highly recommend that you guys use a pencil. I'm using a pen so you can see it, but use a pencil so you can number your axes on this graph. Okay, so between 82 and 92 and between 119 and 148. So what you guys are going to do, your task today is you are going to graph on this plot 3 different types of stable isotopes, 3 different types of isotopes that decay by beta decay, and 3 isotopes that decay by alpha decay, and see if you notice any patterns here. So on this graph, if you guys notice, let's try our first one, 82 protons and 119. This says that it's electron capture. So this is not a stable decay, and this models the process of what happens when we capture electrons, what the new product will be in our isotopes. Okay, we are going to search for isotopes that are stable. So we can do that by adjusting the number of neutrons. So you may have to play around with it until you find a stable isotopes. So, for example, we look at this isotope right here. Has 82 protons, 124 neutrons. This is known as a stable isotope. So we're going to graph that, we're going to plot that, we're going to find 82 and 124, and we're going to plot that isotope, okay? So your task is to plot 3 stable isotopes, 3 isotopes that decay by alpha decay, and 3 isotopes that decay by beta decay. And plot those points, the number of protons on the x-axis and the number of neutrons on the y for each of these. I highly recommend that you color coordinate this so you can look at patterns in your data. So maybe you want to use black for one type of decay and then a different color for another type of decay. You don't have to use the exact same colors that I'm showing here, but you can make a key for yourself and plot these different plots and see if you notice any patterns. Remember, that's what we're trying to investigate here, are patterns. See if you notice any trends for where stable isotopes occur, where alpha decays occur, and where beta decays occur. That's what I want you guys to investigate with this simulation activity. Okay, so once you guys have plotted your points on your graph, let me explain this next part of the assignment. So in the next part, you'll see this table where it says isotope, decay type, balanced nuclear equation, and half-life. So let me show you how to fill this out using one example. There are many examples that you can choose from the simulation. I'm just going to show you one. Okay? So if we look at this particular isotope of radon, see it's radon 219. Okay? This shows that this decays by alpha decay, and it shows a picture of what the products would look like. So in this table, that's the first type of decay that I have to identify. So in the first column, I'm going to write the name of this isotope, radon 219. In the table. And then for the balanced nuclear equation, you'll notice it shows me this equation with the balanced particles on both sides. So this is the part that I'm going to write in the table below. So I'm going to start with the isotope, 219 over 86 radon. Okay, and then that decays, so I'm going to show a little arrow showing that it falls apart. It decays to form 215 on the top, 84, which is polonium, PO. So I'm going to write PO plus our second product here is an alpha particle, which is 4 over 2 He. It's basically a helium atom. So I write 4 over 2 He. So this is the balanced nuclear equation that you get straight from the simulation, and we'll talk more about this in our next lesson. The decay type is alpha. The half-life here is 4 seconds. So you can see that this is a very unstable isotope because half of this isotope decays in 4 seconds, which is not a very long time. So in the last column, half-life, I'm just going to write 4 seconds. You do not have to choose this example. You can choose a different isotope that decays by alpha decay, but that is just one example. You're going to do the same thing for beta, electron capture, and stable. Now for stable, a balanced equation won't be given, so you don't have to worry about the last 2 columns for our stable isotopes. Okay? Then once you guys are done, you're going to answer these questions here. So here is a copy of the graph that I've included, the band of stability graph. This solid line represents a 1-to-1 ratio. Okay, here is the plot points that should look similar to the data we already created in the simulation. Now you'll notice that we have these 3 different regions marked here, indicated on the graph. Region A, this is an area where we have a lot of neutrons, but not as many protons. the neutron is too high. So we're going to shade this in on our notes, and we're going to label area A as areas where beta decay occurs. Region B, notice we have a high number of protons but fewer neutrons, okay? These are too big. So in region B, we have a type of decay called positron emission, and we'll talk more about what that means, okay? Region C is this region that is above 82 protons. So above 82 protons, we have radioactive elements that are too heavy. They have too many protons, and so that's the reason why region C is going to decay using alpha decay. Everything in this region on our graph, we're going to shade in a different color and label this alpha decay because we have too many protons and it becomes unstable. So make sure you guys answer the review questions on the bottom of this page. Make sure you guys think about the patterns. What did you guys notice was the relationship between the number of protons and the number of neutrons and how that relates to the stability of our atom? Because we're going to continue to talk about this for the rest of this week.